Imagine standing on a pier and watching buoys bobbing on the water. If you notice the distance between buoys slowly growing, you might naturally think the water is stretching. But what if, somehow, the buoys were shrinking instead? Would the water still be getting bigger? That little thought experiment gets at one of the surprising things about cosmology. The story we tell about the universe depends on how we measure things. The standard story that the universe is expanding from a hot, dense beginning fits a huge pile of observations, but it's not the only way to interpret some of them. Over the decades, physicists and astronomers have proposed alternatives, ideas where the universe is steady, cyclic, or even shrinking in some sense. Some of these ideas have been ruled out by observations. Some still exist in revised forms. Let me walk you through the main alternatives and why they're interesting, how they try to explain what we see, and where they run into trouble. I'll keep things simple and use everyday analogies, but I'll stick to real science, not science fiction. First, why do we believe in expansion at all? The key pieces are the redshift of galaxies, first noticed by Edwin Hubble, the cosmic microwave background, CMB, and the relative abundances of light elements like hydrogen, helium, and lithium produced in the early universe. Galaxies farther away generally show more redshift. Their light is shifted toward red, which in the simplest view is like a Doppler shift. They're moving away. The CMB is a faint glow of microwave light coming uniformly from all directions. It looks like the cooled remnant of a hot early universe, and is a very characteristic blackbody spectrum. At about 2.7 K, the observed amounts of hydrogen, helium, and trace elements match what we expect from nuclear reactions in a dense, hot early phase. Together these form a strong narrative. The universe began hot and has been expanding and cooling ever since. But redshift alone doesn't uniquely demand expansion. That's where alternative ideas begin. One of the oldest is called tired light. The tired light idea says photons lose energy as they travel long distances through space, perhaps by interacting subtly with matter or fields, so by the time they reach us their wavelengths are longer, redshifted. That could produce a redshift-distance relation without invoking space stretching. It's an intuitively appealing shortcut. The farther a photon travels, the more energy it leaks, so more redshift. Tired light looks neat on paper for explaining a basic redshift distance law, but it fails some crucial tests. One clear test is time dilation in distant supernovae. When an exploding star in a distant galaxy brightens and fades, the whole light curve appears stretched out exactly in proportion to the redshift. That's what expansion predicts. Time intervals also stretch because light travel time and clocks are affected by cosmic expansion. Tired light, on the other hand, would predict a redshifted wavelength but would not naturally stretch the timescales of events unless you add extra ad hoc mechanisms. Observations show the supernova light curves are indeed stretched, matching expansion and not tired light. Another test is the surface brightness of galaxies, how bright they appear per unit area. Expansion dims surface brightness in a very specific way as you look at more distant objects. Tired light does not give the same dimming law. And then there's the cosmic microwave background. The CMB has a nearly perfect blackbody spectrum, and its detailed fluctuations, the acoustic peaks, match predictions from a hot, dense early universe. Tired light has trouble explaining the CMB at all, especially its uniform temperature and the precise pattern of fluctuations. In other words, tired light can be thrown against one observation, but stumbles badly when confronted with the full set. Another historically influential alternative is the steady-state theory championed by Fred Hoyle, Hermann Bondi, and Thomas Gold in the mid-20th century. It grew from a desire for a universe without a beginning, a cosmos that looks the same everywhere and everyone. The steady-state model posited that, as the universe expands, new matter is continuously created so that the average density stays constant. Galaxies would be continuously forming, and the cosmos would have no preferred time. It was a bold philosophical shift. Instead of a single Big Bang, the universe is eternal. Steady-state made testable predictions. which is why it was scientific rather than mere nostalgia for eternity. But the discovery of the cosmic microwave background in 1965 was a killer blow. The CMB looks exactly like the cooled radiation left over from a hot beginning, and matches what we'd expect from an early dense phase after accounting for expansion. Steady-state didn't predict such a background naturally. The steady-state proponents later tried to patch things with variations, quasi-steady-state models that allowed local creation events to produce background radiation. But those fixes were awkward and didn't match the detailed CMB measurements, especially the acoustic peaks and the way the CMB's temperature varies with redshift. Observationally, steady-state lost out to Big Bang cosmology. Plasma cosmology is another idea that's still occasionally discussed, particularly outside mainstream research circles. It emphasizes the role of electromagnetic forces in plasmas, ionized gases, in shaping cosmic structure. After all, plasmas are common in space, and electric and magnetic forces are far stronger than gravity at the particle scale. Hans Ulfvén and others argued that many features attributed to gravity could instead result from large-scale plasma processes and currents. The idea has visual appeal because it uses familiar physics. Filaments, sheets, and loops visible in laboratory plasmas also appear in interstellar gas. The problem is that plasma cosmology does not naturally reproduce the CMB's properties, the success of Big Bang nucleosynthesis, the early universe production of helium and other light elements, or the pattern of galaxy clustering on large scales known as baryon acoustic oscillations. Plasma effects certainly matter for stars, nebulae, and interstellar media, but gravity dominates on the largest cosmic scales, and the success of the Standard Model in predicting the relative amounts of light elements and the fine details of the CMB is a severe constraint. Plasma cosmology ends up unable to explain those signatures without adding complex, ad hoc mechanisms. There are also proposals that don't try to overturn the Big Bang story so much as reinterpret the mathematics. In general relativity, which is our best theory of gravity and space-time, the way you describe expansion depends on choices of coordinates, how you label space and time. One quirky implication is that whether you think of galaxies as flying apart through space or space itself stretching can be a matter of perspective. This coordinate freedom opens a door. If you rescale all your rulers and clocks together, you can transform an expanding metric description into one where the ruler units shrink. In such a view, instead of space expanding, the things you use to measure space might be shrinking. That's a subtle point. Physics doesn't care about absolute sizes, only ratios and relationships. If every physical length, atoms, rulers, molecules, scaled down at the same rate the universe scaled up, you could not detect the expansion. This idea sounds like splitting hairs, but it has real implications. If every measuring device shrank, redshift measurements would be the same as in an expanding universe. Observations only care about relative differences. So some proposed shrinking universe ideas are actually coordinate redescriptions of the same physics. They're not alternative physical theories. They are alternate mathematical descriptions of the same underlying model. To make a physically different claim, that space is shrinking instead of expanding in a way that leads to different physical consequences. You must posit new physics that breaks the scale symmetry. For example, a change in fundamental constants like the electron mass or the fine structure constant that would cause atoms to shrink. That's where the more radical proposals live. Dirac, a legendary physicist, noticed some large number coincidences and speculated that fundamental constants might vary with time. If constants like the gravitational constant g or particle masses changed slowly, atomic sizes and energy levels would change. If atoms were smaller in the past, photons emitted long ago would look redshifted to us, perhaps mimicking expansion. But varying constants theories must confront precise spectral measurements. We can look at light from distant quasars and compare spectral lines that depend on atomic energy levels. These spectra are consistent with our constants being essentially the same across billions of years, within tight limits. Some studies have claimed tiny variations in constants, others find none. Overall, any change must be tiny and carefully constrained. So although varying constants can be invoked to produce redshift-like effects or to recast expansion as Euler shrinkage, the precision of spectral data limits how far that idea can be pushed. Another class of ideas centers on the possibility that general relativity isn't the full story on cosmic scales. Modified gravity theories alter Einstein's equations so that the large-scale behavior of spacetime differs from standard expectations. People have proposed such modifications to explain cosmic acceleration, dark energy, without invoking a mysterious energy component. Some modified gravity schemes produce effects that look like contraction or unusual scale behavior in certain coordinate choices. Others propose that cosmic acceleration is an apparent effect caused by averaging over inhomogeneities. That is, if the universe isn't exactly smooth, the way the expanding geometry is calculated could be misleading. This is called the backreaction idea. Small-scale clumps and voids might influence the large-scale average expansion. Backreaction is interesting because it suggests subtle math might change our interpretation. But making it do the work of explaining observed acceleration, or a hypothetical shrinking, without contradicting other observations is challenging. The effects of inhomogeneities tend to be small, and most detailed calculations show they cannot produce the full apparent acceleration seen in supernova data. Modified gravity theories, like MOND, modified Newtonian dynamics, and more sophisticated relativistic extensions, were initially developed to address galaxy rotation curves without dark matter, and not to replace cosmic expansion entirely. Some modified gravity models can mimic aspects of expansion or acceleration, but they must also respect solar system tests, gravitational lensing observations, the CMB, and structure formation. That's a tall order, and so far no modified gravity proposal has replaced the standard model in all these arenas. Then there are bouncing and cyclic models. These are perhaps the most natural alternatives to a single Big Bang followed by endless expansion. In bouncing cosmologies, the universe undergoes contraction phases that halt at some minimum size and then bounce into expansion again. In cyclic models, this cycle repeats indefinitely. The ekpyrotic universe and certain models from loop quantum cosmology are in this category. In loop quantum cosmology, quantum gravity effects become important at extremely high densities and can create a repulsive force that prevents a singularity and produces a bounce. Such models revive the contracting then expanding picture, a shrinking phase followed by a bounce and expansion. These cyclic ideas have attractive features. They can avoid a singular beginning, and they sometimes offer novel ways to explain problems like the horizon problem, why the CMB is so uniform. But they face challenges too. For example, the detailed pattern of temperature fluctuations in the CMB is well explained by inflation, a period of extremely rapid expansion early on that stretches quantum fluctuations to cosmic scales. Any bounce or cyclic model must reproduce that same pattern. Some cyclic models do propose mechanisms that mimic inflation's effects, but they often require carefully chosen conditions. Observationally, distinguishing a bounce from an inflationary model might be possible if we detect specific signatures, like particular non-Gaussianities in the CMB or specific gravitational wave patterns. So bouncing models remain viable in principle, but they must clear observational hurdles. Roger Penrose's conformal cyclic cosmology, CCC, is another creative twist on cycling universes. Penrose asks what happens if you view the far future of an expanding universe and the far past of a new universe in a way that strips away scale. The end of one eon and the beginning of another could be conformally mapped to each other if mass disappears and only scale-free radiation remains. In CCC, one universe's infinite future becomes the next universe's Big Bang after a conformal rescaling, essentially matching the geometry, but forgetting about absolute sizes. Penrose has predicted certain subtle signals in the CMB, like concentric low-variance rings, which some have claimed to see, though those claims are debated and not widely accepted as conclusive evidence. CCC is fascinating philosophically because it connects eons without a singular boundary, but it relies on speculative physics about how mass disappears and how quantum gravity behaves over huge scales. It's an elegant idea standing on mathematically intriguing but uncertain physics. Let's return to the more concrete tests that distinguish expansion from alternatives. One important test is the Tolman surface brightness test. Imagine you have two identical light sources, one nearby and one very far. In an expanding universe, surface brightness, the light per unit apparent area, falls off with redshift in a specific way. There's a 1 plus z, 4 dependence. Different alternative models predict different dependences. Observations of galaxy surface brightness as a function of redshift match the expansion prediction reasonably well once you account for galaxy evolution. That's a check against tired light and other simple alternatives. Another solid check is the temperature of the CMB as a function of redshift. In an expanding universe, the temperature of the radiation scales as 1/1 plus z. The further back you look, higher z, the hotter the CMB should have been. Astronomers have measured the CMB temperature at different redshifts using atomic and molecular absorption lines in distant gas clouds, and they find the temperature scales in the expected way. That's hard to explain for models that treat redshift as an energy loss mechanism for photons unrelated to expansion. Big Bang nucleosynthesis, BBN, is a particularly constraining observational pillar. The early universe was hot and dense enough for protons and neutrons to collide and form light elements in predictable ratios. The predicted helium fraction, deuterium abundance, and other light element measurements match observations remarkably well across many systems. Any alternative that replaces the early hot dense phase with something else must still reproduce those abundances somehow. Tired light and steady-state models don't have a natural way to produce those primordial nuclear reactions. Bouncing models can reproduce BBN if they include a hot dense phase similar to the standard model during the relevant epoch, but then they are effectively reinstating the key features of the Big Bang. One more observational handle: the pattern of tiny temperature fluctuations in the cosmic microwave background, the acoustic peaks. These fluctuations are the imprint of sound waves in the hot plasma of the early universe, frozen in when the universe cooled enough for photons to travel freely. The positions and heights of these peaks depend on the composition of the universe baryons, dark matter, dark energy, and on the physics of that early plasma. The match between observed peaks and theoretical predictions from the standard model is striking. Any viable alternative must get these peaks right. That's a tall challenge. There's also the idea that what we call expansion could simply be the motion of galaxies through pre-existing space, with no stretching of space itself. That conceptual distinction, expansion of space versus motion through space, is useful to think about. In Newtonian terms, you could picture galaxies flying apart in Euclidean space after some initial push. In general relativity, however, the geometry of spacetime itself evolves. The expansion is built into the metric. Practically speaking, both pictures can often describe the same observations, but certain phenomena, like the redshift of very distant objects and the global geometry, are more naturally explained in the metric expansion language. Whether space itself is stretching or matter is flying through static space can sometimes be a matter of coordinate choice, but not always. The geometry determines how light behaves and how clocks tick, and that leads to observable differences that let us test the models. There are also hybrid ideas, small, creative tweaks that retain much of the Big Bang framework but try to remove uncomfortable aspects, like the initial singularity or the need for inflation. One such line of thought involves variable speed of light, VSL theories. Early on, the speed of light might have been much larger, solving problems like horizon and flatness without standard inflation. If the speed of light varies, though, you must check a huge number of things: atomic spectra, high-energy particle physics, and precision tests of relativity. So far, VSL remains speculative and has not replaced inflation as the preferred solution, in part because inflation predicts specific observable signatures that have been seen. Another more philosophical angle is to ask whether the question itself, is the universe shrinking, is meaningful without specifying physical standards. Science measures ratios. If all lengths, times, and particle masses scaled uniformly, there would be no way to detect that scaling. Physics depends on dimensionless constants. So a shrinking universe that uniformly scales down every physical quantity is observationally equivalent to an expanding universe that scales those quantities up. To make the idea meaningful, there must be differential scaling. Some quantities change while others don't. That's why theories invoking varying fundamental constants are potentially testable. Spectral lines, atomic clocks, and molecular transitions depend on those constants and provide precise ways to check for changes over cosmic time. Now, suppose someone proposes a universe that truly shrinks physically. Space contracts and everything inside it contracts at different rates because different forces respond differently to the change. How would we test that? We'd look for inconsistencies between clocks and rulers, between the behavior of atoms and the propagation of light, between local laboratory physics and cosmological observations. Large-scale tests include supernova light curve stretching, the CMB spectrum and its evolution with redshift, baryon acoustic oscillations as standard rulers, and the primordial light element abundances. So far, the pattern all points to an expanding universe and a hot, dense early state. That doesn't mean creative alternatives are useless. Studying them sharpens the questions we ask and the tests we devise. The history of cosmology shows that sometimes an alternative can push us to better observations that rule it out cleanly, or occasionally suggest an overlooked effect. It's worth mentioning dark energy here, because that's where the expansion story became even stranger. In the late 1990s, observations of distant supernovae showed not only that the universe was expanding, but that the expansion is accelerating. In the context of general relativity, that acceleration can be modeled by a cosmological constant, an energy density of the vacuum that's constant in time, or by a dynamical component like quintessence. Some alternative theories of gravity try to explain the acceleration without dark energy by modifying gravity on large scales. Others suggest the acceleration might be an apparent effect caused by inhomogeneities or by the way we average over structures. None of these alternatives has eclipsed the cosmological constant model observationally. The cosmological constant fits a wide range of data simply and effectively. But the deeper question, what is dark energy physically, remains open. That's why modified gravity proposals are still explored. If we could explain acceleration without invoking an unseen energy component, that would be a major shift. A shrinking universe narrative would have to make sense of acceleration in a new way. If space were contracting globally, we'd need to explain why distant objects appear to be receding faster over time. You could try to invoke changing units or evolving particle masses, but then you must reconcile that with stringent atomic spectroscopy bounds and time dilation of distant events. The experimental constraints are tight, which is why most viable models end up looking a lot like the standard expanding universe picture, even if they're philosophically different. One place alternative models sometimes find traction is in the very early universe, where our observational access is limited and quantum gravity effects could produce surprises. The inflationary model, a short burst of exponential expansion early on, was introduced to solve problems like the horizon and flatness issues, and to provide a mechanism for generating the initial density variations that grew into galaxies. Inflation is an active research area with many models, and some bouncing or cyclic alternatives aim to replace inflation with a contraction-driven mechanism that likewise seeds structure. The trouble is that the specific predictions are delicate. The The statistical properties of the initial fluctuations, their scale dependence, and the presence or absence of primordial gravitational waves are all testable signatures. Upcoming experiments, especially more sensitive measurements of the polarization of the CMB and direct gravitational wave detectors, will help discriminate among competing early universe scenarios. There's also an important philosophical caution. Alternatives should follow Occam's razor in some sense. They should not be more complicated than necessary unless they solve a problem the standard model can't. The standard cosmological model is economical in explanation because a handful of parameters, Hubble constant, matter density, dark energy density, etc., fit a wide variety of observations. Alternatives that require many extra assumptions or special mechanisms to mimic expansion and reproduce the CMB and nucleosynthesis become less compelling, even if not logically impossible. At the same time, science advances by scrutinizing the foundations. Questioning the expansion story led to better observations and deeper understanding. It pushed people to measure supernova time dilation, to study CMB anisotropies in detail, to measure light element abundances in remote gas clouds, and to develop precise tests of fundamental constants. Even proposals that eventually fail are scientifically useful if they motivate new experiments. In that sense, the exploration of shrinking universe ideas or other unconventional models has helped refine the body of evidence that supports the current consensus. It's also useful to separate two things. Could all observable signs be reinterpreted so the universe is shrinking instead? And could the universe have been in a true physical contraction phase at some time? The first is largely a question of coordinate and unit choice. If you rescale everything uniformly, expansion versus contraction can be a bookkeeping change. The second is different. Could the cosmos genuinely have been contracting before a bounce? That's what bouncing cosmologies propose. They're not equivalent to the standard expansion story. Instead, they extend it by adding a prior phase. That possibility remains a legitimate area of research, and it might be accessible to observation via relic imprints in the CMB or in the spectrum of primordial gravitational waves. Finding such an imprint would rewrite parts of the narrative. Finally, let's touch on the role of simulations in structure formation. One reason the standard model is so persuasive is that when you take initial conditions matching the statistical properties we infer from the CMB and evolve them forward under gravity and known physics, you get a universe that looks like ours. Filaments, clusters, voids, galaxies, and so on. Numerical simulations incorporating dark matter and ordinary matter reproduce many aspects of the observed large-scale structure. Alternative theories have to produce similar success. Plasma or electromagnetic-focused models find it difficult to reproduce structure formation over such large scales without invoking dark matter or another mechanism to seed structure. Bouncing and cyclic models can in principle provide the right seeds, but they must do so under the constraints imposed by observed CMB statistics and galaxy surveys. So the alternatives are varied. Some are coordinate reinterpretations, some are tweaks to constants or gravity, some are entirely different pictures like steady state or plasma cosmology, and some are more modest extensions like bouncing/cyclic scenarios. Each makes distinct predictions, and each has to face the observational gauntlet. Time dilation in supernova light curves, the precise blackbody nature and acoustic peaks of the CMB, baryon acoustic oscillations, Big Bang nucleosynthesis, spectral line checks on fundamental constants, and surface brightness tests all provide constraints. When one model fails one or more of these tests, it weakens as a comprehensive replacement for expansion. There's also a human dimension. Scientists are reluctant to abandon an explanatory framework that works well across many domains, but they're always ready to update it if new data demand it. That's how science improves. Models are proposed, predictions are made, and experiments and observations decide which survive. The expansion model has survived many such tests so far, but cosmology remains a living field. New observations, such as more detailed mapping of the CMB, surveys of galaxies across time, and direct detection of primordial gravitational waves, could reveal surprises that force major revisions. While much of the work evaluating alternatives is technical and mathematical, the intuitive picture helps. If an idea claims the universe is shrinking, ask, would such shrinkage change the way atoms and light behave relative to today? Could we measure those changes by comparing spectra from distant objects to nearby ones? Would clocks in remote galaxies appear to run slower or faster? Would the background radiation's temperature change with redshift in a predictable way? If a proposed model can't answer these questions consistently with existing measurements, it's on shaky ground. At the edge of research, new ideas sometimes combine elements of old ones. For instance, some speculative models propose that the universe's metric undergoes complex behavior influenced by extra dimensions or quantum effects, creating phases that look like contraction when viewed from certain perspectives and expansion when viewed from others. Such ideas typically arise in attempts to quantize gravity or unify it with the other forces. They're hard to test at present, but they demonstrate that the conceptual space of cosmology is wide. We can imagine many mathematical possibilities, but only some will match nature. If you're trying to picture why contraction would be hard to see, remember that our measurements are relational. We measure a distant galaxy's redshift by comparing the wavelengths of known spectral lines to the same lines measured in the lab. If the physics producing those lines changes in step with whatever is shrinking, you might not notice anything unusual. But the universe is messy. Different processes depend on different combinations of constants and forces. That gives us multiple, independent checks that make it difficult for a global contraction to hide. It's like trying to hide an elephant under a sheet. If every sheet you bring to the observation is made of the same fabric that also shrinks, the elephant might hide. But nature gives you a variety of measurement sheets: atomic clocks, supernovae light curves, microwave background photons, element abundances, and making the elephant disappear under all of them simultaneously is extremely difficult. One of the most interesting fronts for testing alternatives is gravitational waves. These ripples in spacetime are produced by violent events like black hole mergers, and the primordial universe could have produced a background of gravitational waves with characteristic spectra. Inflation predicts a certain pattern for primordial gravitational waves, and some bouncing or cyclic models predict different patterns. Measuring the amplitude and spectrum of primordial gravitational waves would provide a direct probe of the very early universe and could favor one class of models over another. Experiments like pulsar timing arrays and future space-based detectors aim to reach the sensitivities needed to test those ideas. Another experimental avenue is ever more precise tests of fundamental constants using atomic clocks. Laboratory clocks have become so precise that they can detect incredibly tiny drifts. If constants like the fine structure constant or the electron-to-proton mass ratio were varying over cosmic time, sensitive astronomical observations combined with lab experiments could detect or constrain that. So far, the constraints are tight, which puts pressure on theories that try to explain cosmic redshift as a consequence of changing atomic properties. So when people ask, what if the universe is actually shrinking? It's legitimate to respond on several levels. On a purely coordinate level, the language of shrinking can be a reinterpretation of the same physics. On the level of physical proposals, there are real, testable models that try to replace expansion with other mechanisms: tired light, steady state, plasma cosmology, varying constants, modified gravity, and bouncing universes, among others. Many of those have been falsified by observations like the CMB, time dilation of supernovae, and light element abundances. Others remain viable alternatives in certain forms, but they must match the full suite of observations that the standard expanding Big Bang model already explains. That's a high bar. There's a productive tension between conserving successful explanations and remaining open to new frameworks. Scientific progress often comes from re-examining assumptions, proposing radical alternatives, and then confronting them with data. The alternatives to expansion have pushed cosmologists to make more precise measurements and to think carefully about the assumptions behind our interpretations. Whether those alternatives ultimately survive, get folded into improved versions of the standard model, or fade away, they've played an important role in guiding inquiry and sharpening our understanding. Let's follow that thread a bit deeper. What would it really take, physically, for a shrinking universe hypothesis to hide in plain sight? The heart of the matter is this: most of what we measure in cosmology comes from comparing different things. We compare the color of light from a distant galaxy to the colors produced by atoms in our lab. We compare how long a supernova takes to brighten and fade to how long similar events take nearby. We compare the size of a pattern imprinted on the cosmic microwave background to the size of the same pattern seen in the distribution of galaxies. Those comparisons are powerful because they involve combinations of quantities that often cancel out simple relabelings of units. To hide a global shrinking while keeping those ratios unchanged, you'd need the shrinkage to affect many independent physical systems in the same coordinated way. That's a tall order. Think about an everyday analogy. You and a friend agree on a unit of length, say a meter stick. If your meter stick slowly shrank while everything else stayed the same, you'd notice objects around you getting longer relative to your stick. If every object, the chair, the house, your friend, also shrank exactly in proportion, you wouldn't notice any change locally. But now imagine you have a clock and a candle. If the clock's tick rate and the candle's burn time both scale the same way as lengths, you still wouldn't notice. Reality gives us many independent meters and many independent clocks. Atoms, molecular transitions, geological dating, stellar lifetimes, orbital periods, supernova-like curves, radio pulsars, and so on. For a universal shrinkage to hide from all of these, it would have to act on them with incredible coordination, or it would have to change only dimensionful quantities while leaving all measurable dimensionless ratios fixed. That last possibility is the technical loophole. Dimensionful numbers, like a length measured in meters, can be redefined by a unit change. Dimensionless numbers, pure ratios such as the fine structure constant, the proton-to-electron mass ratio, or the ratio of two spectral line frequencies, are the real observables. If those are constant, you can often redescribe physics as either shrinking rulers or expanding space. But if any dimensionless constant changes, that's physically detectable. Which dimensionless numbers matter most? Two of the most commonly discussed are the fine structure constant, alpha, and the ratio of the proton mass to the electron mass, mu. The fine structure constant governs the strength of electromagnetic interactions and sets the spacing of atomic spectral lines. The proton-to-electron mass ratio affects molecular vibration and rotation energies, which govern many of the lines astronomers use to probe distant gas clouds. If alpha or mu changed across cosmic time, light from distant quasars and galaxies would show shifts in the relative positions of different spectral lines, not just an overall redshift. Astronomers have looked for these fingerprints. Some early studies hinted at tiny spatial or temporal variations, but more thorough, precise surveys tend to find consistency with constancy to very high precision. There are active debates and ongoing work, but the bottom line is that any variation must be tiny enough to fit into narrow experimental windows. Another powerful probe comes from a surprising source: a natural nuclear reactor that operated about 2 billion years ago in Oklo, Gabon. Certain isotope ratios preserved in the reactor's remnants are sensitive to the position of nuclear resonances, which in turn depend on fundamental constants. The Oklo data constraint changes in alpha to be extremely small over those 2 billion years. Combine that with precise laboratory tests today, atomic clocks compared over years, and you get limits on drift rates of constants that are unbelievably tiny, often quoted in parts per trillion per year or better for some constants. Those constraints significantly restrict models where particles or forces evolve in time in ways that would cause atoms to uniformly shrink. Geology and radioactive dating provide another independent check. Radioactive decay rates depend on nuclear physics. If the underlying constants drifted, the rates would change, and our dating of rocks and meteorites would be inconsistent. The remarkable agreement between different dating methods, uranium lead, potassium argon, rubidium strontium, across a range of timescales is another sign that fundamental rates haven't wandered much. Similarly, stellar astrophysics offers constraints. Stars shine because of nuclear fusion, and their lifetimes and spectra depend on particle masses and interaction strengths. Observations of stars across the universe, including very old stars and those in distant galaxies, show patterns consistent with standard physics and stellar evolution models. If atoms had been appreciably different in the past, stellar spectra and lifetimes would betray that. Let's consider the cosmological rulers astronomers use: supernovae, the baryon acoustic oscillation scale, and the acoustic peaks in the CMB. These are not arbitrary. They're tied to specific physical processes in the early universe. The baryon acoustic oscillation, BAO scale, arises from sound waves in the hot plasma before atoms formed. Those sound waves travel a fixed comoving distance set by the conditions in the early universe, essentially the size of the sound horizon at decoupling. That scale shows up as a preferred separation between galaxies today, and we can measure it at different redshifts. The CMB gives us a snapshot of the early plasma and the sound horizon directly. The BAO gives a complementary, later time measure of the same anchor. If a shrinking universe scenario changed rulers and rods arbitrarily, the two should disagree. The consistent, mutually reinforcing measurements of distances from CMB, BAO, and supernovae argue strongly that we are not being fooled by a simple global rescaling of rulers. There's also the issue of time. If atomic energy levels change, clocks based on those transitions tick at altered rates. We have atomic clocks on Earth that now reach fractional inaccuracies of order 10⁻18 in a few hours. These clocks can be compared across continents using optical fibers and satellites, and they track tiny differences. Extrapolate that precision across decades and across the light travel time to certain astrophysical objects, and we get more constraints. Pulsars, rapidly spinning neutron stars, provide cosmic timekeepers. Millisecond pulsars, in particular, spin with very stable periods and can be timed with microsecond precision over years. If fundamental physics changed significantly over cosmic timescales, pulsar timing arrays would eventually notice inconsistencies with predictions based on constant physics. So far, pulsars behave as expected within tight bounds. Now let's think about dynamics. What if the metric of spacetime itself were contracting? In a simple, homogeneous contraction, light waves traversing contracting space would get compressed, blue-shifted, not redshifted. So if the global metric is simply shrinking, the light from distant galaxies would appear bluer, not redder. The observed redshifts of galaxies make a straightforward contracting metric impossible unless something else is in play. That's why the naive picture of space shrinking doesn't fit the facts. To match observed redshifts while claiming shrinkage, you need an asymmetry. The things emitting light in the past must be different from what we measure locally in a way that makes their emitted wavelengths appear longer relative to our standards today. In other words, either the emitter's physics changed, or the way photons travel changed. And these alternatives are where researchers focus when they consider non-standard stories. One route physicists explore involves scalar fields that couple differently to different sectors of the standard model. A scalar field is just a field characterized by a number at every point in space and time, like temperature in a room. If such a field evolves slowly over cosmological time and interacts with, say, the electron mass but not with the proton mass in the same way, then the proton-to-electron mass ratio would shift. That would change molecular spectra in a characteristic way. The old universe's atoms would then emit photons with different relative frequencies than today's atoms, producing an apparent redshift in the spectral pattern even if the metric were not expanding. Those models are mathematically allowed but must thread a needle. The coupling strengths and evolution of the scalar have to be chosen so that they produce the observed redshift distance relation, and all the other tests match. As we've said, spectroscopic surveys of quasars and molecular clouds tightly constrain how much things like mu can change, shrinking the allowable parameter space for such scalar-driven schemes. A closely related theoretical nuance concerns conformal frames, ways of writing the equations of gravitation and matter interactions, so that what looks like a change in the scale of spacetime in one frame looks like a change in particle masses in another. This is often discussed in Jordan frame versus Einstein frame language in scalar tensor theories of gravity. The physics is the same, but the bookkeeping differs. In one description, the metric evolves a certain way. In another, the metric looks different but particle properties vary. This is a useful reminder that how we present things can sometimes hide or highlight physical effects, and it's the frame-invariant, measurable quantities that ultimately matter. That said, if a model predicts that dimming of distant objects or the time dilation of supernova light curves would be altered, that's an observable signature independent of the frame used to describe it. Let's step back and ask about the survival of structure under a hypothetical shrinkage process. Galaxies, stars, and planets are held together by gravity and electromagnetism at the atomic level. If every length scale contracted uniformly slowly, gravitationally bound systems would largely be unaffected because gravity is scale-free in Newtonian terms. The dynamics depend on dimensionless ratios like Gm/RC2 for relativistic corrections. But if the contraction affects particle masses or the speeds of waves, including the speed of light, differently from gravitational constants like g, then bound systems could shift. Consider planetary orbits. If the gravitational constant g changed, while masses and lengths changed differently, orbital periods would alter, and the precise motions of planets would no longer match predictions. Lunar laser ranging, bouncing lasers off reflectors left on the Moon, measures the Earth-Moon distance to millimeter accuracy and has tracked it for decades. Those data are sensitive to any slow drift in the Earth-Moon separation that's not tied to known tidal effects. They put stringent bounds on any hypothetical drift in gravitational coupling or in the size of local rulers. We should also highlight an important conceptual distinction that sometimes confuses non-experts: local versus global behavior. Cosmological expansion describes the large-scale metric. Distances between unbound objects increase. But local physics in a laboratory or inside a galaxy doesn't necessarily follow the same simple scaling because those regions are dominated by local forces. If you suspend a ball in a laboratory and the homogeneous cosmological expansion were somehow significant at that scale, you might wonder whether the ball's size would change. In reality, electromagnetic forces in matter overwhelmingly override the extremely weak tidal influence of cosmic expansion at small scales. That's why atoms don't expand along with the universe, and why the solar system remains tightly bound. Any shrinking scenario that claimed atoms contract, while larger scales do not, would therefore need to specify a microscopic mechanism that acts selectively on different scales, again, a challenging requirement. We've been circling observational tests, so let's give some concrete examples of the kinds of experiments that can distinguish expansion from a crafty shrinking alternative. One is the Tolman surface brightness test I mentioned earlier. In an expanding universe, surface brightness dims with redshift following a 1 plus z4 law. That law arises from two effects: redshift of photon energies and time dilation. Fewer photons per second arrive, plus the stretching of observed areas combined. If photons lose energy by some other mechanism, like tired light, you'd get a different dimming law. Another example is supernova time dilation. The measured light curves of distant type Ia supernovae scale in duration exactly as 1 plus z, matching expansion. If emission processes themselves changed in such a way as to mimic this dilation, you'd need a contrived mechanism that affects timing and energy in just the right correlated way. Then there's the CMB temperature-redshift relation. The radiation's temperature scales as 1 plus Z because expansion cools the photon gas. Astronomers measure the CMB temperature at different redshifts by observing the excitation states of certain atomic and molecular species in intervening gas clouds. Those excitation patterns depend on the radiation temperature. Measurements to date are consistent with the expected scaling, again posing a challenge to non-expansion interpretations unless they can reproduce this temperature behavior by alternative means. Another observational program relevant to this discussion is the search for primordial gravitational waves. Inflation predicts a background of gravitational waves with a particular spectral shape and amplitude related to the energy scale of inflation. Bouncing or cyclic models often predict very different gravitational wave signatures. The pattern of polarization in the CMB, especially the so-called B modes, carries information about primordial gravitational waves. Experiments targeting B modes, along with direct detectors like LISA and pulsar timing arrays, have the potential to tell us whether the early universe underwent inflation, a bounce, or some entirely different dynamical history. If a shrinking era preceded our current expansion via a bounce, that history could be written into the primordial gravitational wave background. What about the Hubble tension, the discrepancy between measurements of the Hubble constant using nearby indicators, Cepheids and supernovae, and the value inferred from the CMB? Some people have wondered if exotic local dynamics or a misinterpreted expansion could explain the tension. Could a shrinking scenario help? Generally speaking, no simple shrinking hypothesis resolves the Hubble tension without creating conflicts elsewhere. The tension might point to new physics in the early universe, affecting sound horizons, and thus the CMB inference, or to systematics in the distance ladder. But a wholesale reinterpretation of cosmic expansion as shrinkage tends to swap one set of conflicts for another. That said, the Hubble tension is an active area of research where creative ideas are being explored, and any plausible new theory must satisfy the full complement of cosmological constraints. Beyond observational tests, theoretical consistency matters. If you invent a mechanism that makes atoms shrink relative to space, you need to embed that mechanism in a coherent physical framework that respects conservation laws, quantum mechanics, and the known interactions. Scalar fields that slowly evolve, changing particle masses via couplings, are a popular theoretical device because scalar fields appear naturally in many attempts to extend the standard model and in models of dark energy. They provide a mathematical playground for constructing controlled variations. But they also introduce potential problems. They can mediate new fifth forces that would show up in precision tests of gravity unless the coupling is finely tuned or screened in dense environments. Theories need to explain why we haven't observed such forces in laboratory and solar system tests, or propose mechanisms like chameleon screening that hide the field's effects locally while allowing cosmological evolution. There's also the question of entropy and the arrow of time. An expanding universe with low entropy initial conditions naturally provides a direction of time and a framework for the growth of structure and the thermodynamic behavior we observe. Some contracting or cyclic models must confront how entropy is handled across cycles or bounces. If the universe shrinks and then bounces, does entropy increase steadily? How do you pass from a high-entropy distant past to a low-entropy hot Big Bang? Proposals such as Penrose's conformal cyclic cosmology try to address this by invoking the eventual dilution of mass and the dominance of scale-free radiation. But those ideas rely on speculative aspects of quantum gravity and black hole thermodynamics. Any credible shrinking-based cosmology must offer an account of entropy and thermodynamic evolution consistent with what we see. Let's make it concrete with a thought experiment that clarifies the interplay between dimensionful units and observables. Suppose someone claims that everything in the universe, rulers, atoms, the meter, the second, even the speed of light, shrinks at 1% per billion years. Locally, you would never notice. Your meter stick, your clock hands, and your body would shrink together. But dimensionless ratios like the fine structure constant would remain unchanged, so atomic spectra would look the same. Even so, comparisons across different epochs that rely on processes not tied to the shrinking would fail. For example, radioactive decay-based dating of meteorites compared with thermodynamic cooling rates of the Earth's mantle, or with distant stellar evolution patterns, would diverge unless all those processes shrink identically. In practice, we have so many different, independent kinds of clocks and rulers across physics and astronomy that arranging uniform shrinkage is effectively impossible without making the shrinkage a mere redefinition of units. When a proposed model reduces to a unit redefinition, it stops being a distinct physical theory and becomes a change of language. Now consider a different thought experiment. Imagine a scalar field causes electron masses to shrink slowly over time, while proton masses remain essentially constant. Atomic sizes, which depend roughly on the inverse of the electron mass times the fine structure constant, would change. Molecular spectra would shift in a way that is detectable when comparing multiple lines. Quasar absorption line systems, with high-resolution spectroscopy, would reveal the mismatch. This is the realm of observational constraints. Different spectral transitions have different dependencies on alpha and mu, so by comparing many transitions you can isolate changes in constants. That's why large, precise spectroscopic surveys of quasars and molecular clouds are so valuable. They don't just measure redshifts, they test the constancy of the underlying physics. If you look at the historical arc of cosmology, exploring such alternatives has had a practical benefit beyond the pleasure of intellectual variety. The attempt to test tired light or steady-state hypotheses motivated experiments that didn't just rule those ideas out. They sharpened the techniques we use to probe the universe. Measuring supernova light curve time dilation, mapping the CMB in exquisite detail with satellites like COBE, WMAP, and Planck, checking the surface brightness redshift relation, studying baryon acoustic oscillations. These were not exercises in cosmological dogma but scientific tests responding to real alternative claims. That's how the field has matured, by converting conceptual possibilities into observations. It's also worth noting that some proposed alternatives don't deny expansion so much as reframe parts of it or ask deeper questions about its origin. For instance, inflationary cosmology is a theory that supplements the expanding Big Bang picture with an earlier epoch of accelerated expansion. It explains why the CMB is uniform across the sky and why the universe is spatially flat to high precision. But inflation brings its own puzzles and motivates searches for signals such as primordial gravitational waves. Similarly, bounce or cyclic theories often try to remove the singularity at the beginning of time and replace it with a prior phase. Those ideas don't necessarily deny the later expansion we observe. Rather, they provide a different prehistory. So when talking about shrinking universes, it's useful to keep straight whether we're discussing literal global contraction visible today, or a prior contracting phase in a cosmic cycle, or mere coordinate/units transformations that reframe the same expansion into a different language. What about extreme hypothetical cases where contraction is localized? You could imagine exotic scenarios where certain regions of space shrink relative to others due to inhomogeneous fields or phase transitions in exotic matter. Those would likely leave telltale imprints. Gravitational lensing anomalies, anisotropies in the CMB, localized systematic offsets in spectral properties of galaxies, or unexpected tidal signals in gravitational wave detectors. Observational cosmology is getting so precise that small, regionally varying departures from the standard model are becoming accessible. Surveys that map millions of galaxies across cosmic time, CMB polarization experiments, and large-scale gravitational wave observatories will increasingly constrain such patchy alternatives. Finally, looking forward, the technology for detecting tiny deviations from standard physics is improving rapidly. Next-generation optical and radio telescopes, more precise atomic clocks, long baseline interferometers, space-based gravitational wave detectors, and deeper cosmological surveys will either continue to affirm the standard model with ever-tightening error bars or uncover anomalies that push theory in new directions. Projects like the James Webb Space Telescope, Euclid, the Dark Energy Spectroscopic Instrument, DAISY, CMB Stageminus 4 experiments, and LISA expand the parameter space we can test. If any hint of non-standard shrinkage or varying constants exists, this new generation of instruments has a good chance of finding it. So if someone asks whether a shrinking universe is possible, a helpful response is to separate three things. 1. Trivial redescriptions that change only our units or coordinate labels, which aren't physical alternatives. 2. Physically distinct models that alter particle properties or interactions in ways that could mimic aspects of expansion, but are constrained by myriad observations. And 3. Dynamical histories that include contraction phases, bounces, or cycles that may precede our observable expansion and could leave subtle observable imprints. The evidence accumulated so far favors a simple narrative. The universe has been expanding from a hot, dense past, punctuated possibly by inflation or other early universe dynamics, and currently accelerating due to dark energy. But that verdict is empirical, not dogmatic. The alternative ideas we've discussed have played and continue to play a crucial role in forcing that verdict to be tested in many independent ways. As we keep pushing on these frontiers, two strategies stand out for distinguishing shrinking-like alternatives from the standard picture. One is to look for inconsistencies across independent probes. For example, a mismatch between CMB-derived and Bow-derived distance scales that cannot be blamed on calibration errors. The other is to look for anomalies in fundamental constants using both laboratory and astrophysical systems that depend differently on those constants. The combination of high-precision local experiments and high-fidelity cosmological observations is a powerful cross-check. If a creative shrinking model wants to remain viable, it must survive both kinds of scrutiny simultaneously. What's fascinating is how these investigations reveal the deep unity of physics. Questions about the size of atoms, the ticking of clocks, the spin of pulsars, the glow of the CMB, and the motion of galaxies are not isolated curiosities. They're all interconnected. A claim that the cosmic rulers are changing impacts chemistry and geology, nuclear astrophysics and planetary motion, as well as high redshift cosmology. That web of connections is why cosmology has evolved into a precision science. Even bold, seemingly far-fetched alternatives have to pass through lots of different empirical gates, and those gates are closing in because of ever-better measurements. If you like puzzles, this is a good one to watch. The question, could the universe be shrinking, forces us to think carefully about what we measure, why we interpret it as expansion, and how theoretical models map onto observable signatures. It clarifies why dimensionless constants are central, why independent cross-checks matter, and why the standard expanding universe model has survived despite many attempts to overturn it. At the same time, the tug-of-war between bold ideas and relentless observation is exactly how science progresses. Every alternative that fails leaves behind a clearer understanding and better tools. Every alternative that survives, even barely, points toward new experiments and new ways to probe reality. So let's press the question further. If someone wanted to make a physically meaningful model in which the universe is genuinely shrinking in one way or another, what would they have to put on the table? What are the concrete ingredients, mechanisms, and observational signatures that would make such a model credible rather than merely a change of labels? Working through this helps clarify why most simple, shrinking stories fall apart, and where the interesting, testable possibilities actually sit. A good place to start is by listing the minimal demands any serious shrinking model would face. First, it has to reproduce the redshift distance relation we observe, not just roughly, but with the detailed dependencies we measure across many different kinds of sources. Second, it has to explain the observed time dilation of distant events, like Type Ia supernovae, that scales as 1 plus z. Third, it must account for the cosmic microwave background spectrum and its thermal history, including how the CMB temperature evolves with redshift. Fourth, it must either reproduce the light element abundances produced by Big Bang nucleosynthesis, or provide a different, equally compelling mechanism that makes the same abundances. Fifth, it must match the acoustic peak pattern in the CMB and the baryon acoustic oscillation scale seen in galaxy surveys. Sixth, it must survive local tests. Precision laboratory experiments, solar system measurements, pulsar timing, lunar laser ranging, geological and meteoritic dating, and constraints from natural reactors like OCLO. Seventh, it should ideally be embedded in a consistent theoretical framework that doesn't break quantum mechanics, energy conservation, or well-tested parts of particle physics, unless it offers a clear and testable replacement. That is a long checklist. Let's unpack the broad strategies someone might use to try to tick these boxes, and what each strategy would imply observationally. One broad strategy is to tinker with the things that set atomic and molecular scales. An atom's size and the energy of its spectral lines depend on the electron mass, the charge of the electron, and Planck's constant. In practice, on combinations that form dimensionless numbers like the fine structure constant, alpha, or the proton-to-electron mass ratio, mu. If a scalar field pervading the universe couples to electrons in such a way that the effective electron mass changes slowly with cosmic time, then all atomic transitions would shift in wavelength as that field evolves. If the field evolves right, emissions from atoms billions of years ago might look redder to us today, even if the metric of spacetime itself did not stretch. That trick is attractive because it gives a physical mechanism for producing redshift-like effects without literal metric expansion. But you quickly run into the observational web. Different types of spectral lines depend differently on alpha and mu. By comparing many lines from many elements and molecules in distant quasar absorption systems, astronomers can separate an overall wavelength shift, a redshift, from relative changes in line positions caused by shifts in the underlying constants. So a scalar field-induced mass change would leave a fingerprint, mismatched line ratios, which is precisely what surveys have been looking for. The upshot is that any mass-evolving model must either make those relative shifts tiny, well inside current limits, or find a specific coupling pattern that makes the shifts mimic a pure redshift across all the relevant transitions. That latter option is theoretically contrived and tightly constrained. A related approach is to suppose that some constants vary while others don't, or that the speed of light changes over cosmic time. Variations in the speed of light, VSL, have been proposed to tackle problems like the horizon problem that inflation addresses. If c were larger in the past, signals could have traveled further, making the early universe more homogeneous. But VSL models must address a huge array of consequences. Maxwell's equations, atomic spectra, the relationship between energy and frequency, and Lorentz invariance, the symmetry underlying special relativity, all rest on the constancy of c. Thus, VSL proposals usually require reformulating fundamental physics carefully, and they are subject to severe experimental tests. Atomic clocks, high-energy astrophysical observations, and terrestrial tests of Lorentz symmetry all limit how wildly c can have changed. So again, the room for VSL to masquerade as shrinkage is narrow, unless it's buried in exotic, well-hidden physics. A more subtle, mathematically elegant path is to exploit a symmetry called conformal invariance, or scale invariance. If the fundamental laws of physics were exactly conformally invariant, meaning they don't care about absolute sizes and can be rescaled without changing the physics, then the notion of absolute expansion or contraction would be empty. Everything could be rescaled arbitrarily, and only dimensionless ratios would have meaning. The trouble is that our universe is not conformally invariant. Masses exist, length and time scales show up in physics, and dimensionless constants like alpha have specific values. To build a shrinking model that's more than a bookkeeping exercise, you must introduce dynamics that break conformal invariance in a controlled way, or else explain how masses and other scales emerge from a deeper, scale-invariant theory at the right moments. Penrose's conformal cyclic cosmology leans on conformal ideas in a creative way, but it requires speculative dynamics about how mass effectively disappears in the infinite future. That idea is daring and interesting, but it's also challenging to test cleanly. Another class of possibilities changes gravity itself. If the equations that relate matter and spacetime differ on cosmic scales from Einstein's general relativity, then the metric could evolve in unfamiliar ways. Modified gravity models come in many flavors. Some modify the way curvature responds to energy, others add new degrees of freedom, often scalar fields, or extra dimensions. Certain modified gravity setups can make local physics look like the usual physics, while altering cosmology in ways that mimic accelerating expansion or produce peculiar scaling behavior. But a perennial problem for such theories is screening. The new degrees of freedom that change gravity on cosmological scales typically would produce observable fifth forces or affect solar system dynamics, unless they are suppressed locally by mechanisms like the chameleon effect. Screening mechanisms are clever and have been studied extensively, but they are not free. They predict their own signatures, often in precision laboratory tests and in the behavior of compact astrophysical objects. So modified gravity can be used to craft models with unusual scale behavior, but those models have to simultaneously clear a dense gauntlet of tests. If someone tries to make a literal contracting metric reproduce the observed redshift, they face a basic sign problem. In a simple, homogeneous contraction, light traveling toward us gets blueshifted, wavelengths shorten, not redshifted. So to make blueshifting geometry appear redshifted, you need a compensating effect. That compensation could be, for example, evolving emission physics where the emitters in the past produced longer wavelengths, or an interaction during photon propagation that systematically increases wavelengths. These are essentially the tired light type fixes, which, as we've discussed before, struggle with other tests like time dilation and the CMB's blackbody nature. Any shrinking metric story that wants to be consistent with observed redshift would therefore need to include rather specific, correlated mechanisms for changing emission and propagation properties, and those mechanisms themselves must obey the web of crosschecks. Let's look at the cosmic microwave background again from the shrinking model angle, because the CMB is such a stringent diagnostic. The CMB's blackbody spectrum is extraordinarily precise. Deviations are limited to tiny mu and y distortions. If photons changed energy en route due to interactions with a medium or field, a tired light kind of effect, you'd typically create spectral distortions. The same applies if you produce photons at different energies, because atomic levels were different in the past. Unless everything is orchestrated perfectly, the shape of the spectrum and its scaling with redshift would be affected. Moreover, the acoustic peak structure, the series of hot and cold spots at particular angular scales, encodes the physics of sound waves in the early plasma. That pattern depends on the ratio of baryons to photons, the total matter content, and the expansion history around recombination. A credible shrinking model needs to reproduce that detailed pattern. It can try, for example, to posit a hot dense phase at early times, so it's not trying to avoid the Big Bang so much as reframe it. Or it could attempt to generate the peaks by an entirely different mechanism. Either way, matching the peaks is a tall order and a useful sieve. Big Bang nucleosynthesis, BBN, is another unforgiving test. The produced amounts of helium-4, deuterium, and lithium, in broad strokes, emerge from nuclear reactions happening when the universe was a few minutes old and at temperatures of tens of keV. If you don't have a comparable hot, dense early phase or a mechanism that recreates those reaction rates, it's hard to see how you end up with what we measure. Some bouncing or cyclic models include an early hot period that functions like the standard Big Bang for nucleosynthesis. in which case they aren't denying the early hot phase. They're extending the history to include what happened before it. But if you aim to avoid the hot dense stage and still claim to reproduce BBN abundances, you have to propose a viable, testable set of nuclear reactions under different conditions. That is rarely simpler than just accepting a hot early phase. A practical way to think about distinguishing shrinking-like models from standard expansion is to look for mismatches between independent rulers and clocks. The cosmic toolbox contains several independent distance indicators: supernovae, standardizable candles; baryon acoustic oscillations, standard rulers; gravitational lensing, and geometric methods built on parallax or time delays in strongly lensed quasars. There are also independent clocks: atomic transitions in the lab, pulsar timing, radioactive decay, stellar evolution timescales, and cosmological probes like the CMB temperature at different redshifts. If a theory says rulers are shrinking, check whether the distances inferred from standard rulers, BAO, agree with distances inferred from standard candles, supernovae, and from the CMB-derived scale. Similarly, if atomic clocks are changing, see whether pulsar timing and geological dating tell the same story. Any inconsistency is a crack that can expose the model. That method of cross-comparison is why cosmology today is so powerful. It doesn't rely on a single kind of measurement. It relies on a network of mutually constraining observations. It's relatively easy to invent a mechanism that can spoof one observable. It's much harder to spoof many different, independent observables simultaneously without fine-tuning. Let's dig into some specific niche signatures a true shrinking model might leave behind, things we can look for now or in planned experiments. One obvious class is spectral anomalies. If atomic masses evolved, the relative positions of spectral lines from different species would change in a predictable way. High-resolution spectroscopy of quasars and molecular clouds is already sensitive to such effects. Surveys with high-stability spectrographs on large telescopes, such as the ESO's Espresso instrument on the VLT and future spectrographs on extremely large telescopes, will push sensitivity to fractional changes in alpha or mu at the parts per million or better level. Any credible model that relies on changing atomic parameters must live within these narrow bands, or it will be detected. Another set of signatures involves photon number conservation and spectral distortions of the CMB. If photons are lost or their energy is changed during propagation, the CMB's Planckian spectrum will be distorted. Observations by Kobe constrained such distortions to be tiny. Future experiments could do even better. So a shrinking model that needs photon energy changing processes to mimic redshift faces a tight limit. Those processes must preserve the CMB's blackbody spectrum to very high accuracy. Surface brightness tests provide a different lever arm. In expanding universes, surface brightness falls off with redshift as 1 plus Z4. Tired light scenarios do not reproduce this decline correctly. Accurate measurements of galaxy surface brightness across redshift, especially when corrected for galaxy evolution, therefore test non-expansion hypotheses. Time dilation in supernovae is another hard-to-fake signature. Expansion predicts that all time intervals are stretched by the same factor, 1 plus z. If a model claims redshift comes from changing emitters rather than metric expansion, it must explain why the durations of distant supernovae are stretched in lockstep with their spectral redshifts. That requires a tied mechanism affecting both energy and timing in a correlated way, which is uncommon and contrived. Gravitational waves open a new, increasingly sharp observational window. The frequency evolution of gravitational wave signals from distant inspiraling binaries carries information about the expansion history, and potentially about whether the speed of propagation of waves or gravitational coupling has evolved. Space-based detectors like LISA will observe inspirals at lower frequencies and could detect cosmological backgrounds. Pulsar timing arrays are already probing nanohertz gravitational waves and have reported intriguing hints of a stochastic background. Different early universe scenarios, inflation, a bounce, phase transitions, predict different gravitational wave spectra. If the universe had a contracting phase, or if unusual coupling to fields changed wave propagation, that would show up in the shape or amplitude of the gravitational wave background. So gravitational wave astronomy is a promising way to probe deep-time cosmological dynamics that could distinguish expansion versus shrinkage stories, or reveal a prior contracting epoch. Precision local experiments continue to matter. Atomic clocks now reach fractional stabilities below 10⁻18 in short times, and comparisons spanning years constrain drift in fundamental constants. Laser ranging to the Moon constrains changes in the Earth-Moon separation and the effective gravitational coupling. Torsion balance experiments test the inverse square law at short distances and search for fifth forces. All of these laboratory and solar system tests limit how a hypothetical shrinking mechanism could act without showing up locally. A viable shrinking model must incorporate a screening or localization mechanism that hides cosmological evolution from local experiments, and that hiding mechanism itself usually has testable consequences. Another subtle but informative class of tests involves big-picture energy accounting and entropy. If the universe were genuinely shrinking, what happens to entropy? The second law of thermodynamics, that entropy tends to increase, is deeply tied to the arrow of time in cosmology. Many bouncing and cyclic models grapple with entropy across cycles. If entropy always increases, how can the universe undergo repeated similar cycles without piling up entropy? Proposed resolutions include mechanisms that remove or redistribute entropy between cycles, or that redefine how we measure entropy in regimes where mass becomes negligible and radiation dominates. These resolutions often touch on black hole physics too. Black hole evaporation and the fate of information could influence how entropy behaves on the longest timescales. So a shrinking cosmology aiming to be complete must not only match spectral lines and supernova light curves, it must offer a coherent thermodynamic story, which is non-trivial. There's also an instructive sociological point about why so much research focuses on variants of expansion rather than wholesale shrinkage. The standard lambda-CDM, cosmological constant plus cold dark matter model, is phenomenally successful across many domains with a compact set of parameters. Changing it wholesale requires introducing many new degrees of freedom and detailed mechanisms, which raises the bar for the new theory. That does not mean one should never invent such theories. Indeed, creative ideas have pushed the field forward. But it does mean that the natural conservative path is to seek minimal, testable departures that explain specific anomalies. This is why many researchers concentrate on questions like the nature of dark energy or the Hubble tension. They work within the expanding universe framework but probe its edges. Shrinking models tend to be radical. Radical proposals have to survive radically thorough testing. At the same time, the history of cosmology shows that taking alternative ideas seriously has practical benefits. Testing tired light led to the supernova time dilation measurement. Debates about steady-state motivated deeper study of the CMB. Questions about varying constants spurred the development of ultra-stable spectrographs and atomic clocks. So exploring shrinking-like hypotheses often pays dividends by sharpening instruments and experiments that have broader uses. There's a philosophical layer too, one that scientists often skirt, but that helps keep thinking honest. The distinction between coordinate transformations and physical change is pivotal. You can always rename your rulers and your clocks and make the universe look like it's shrinking or expanding. That's the point made earlier about units. What matters is what you can measure as a ratio of two independent physical quantities. For example, the ratio between two spectral lines depends on fundamental constants. If that changes, it's physical. If everything changes in perfect lockstep, then nothing physically detectable has happened. You've merely changed human bookkeeping. That idea goes back to relationalism. Physics teaches us about relations between things, not absolute sizes. It's a powerful, clarifying viewpoint. If a shrinking model wants to assert a real physical change, it must produce a change in relations that is observable. Otherwise, it's just a different language for the same world. Let me give a concrete, slightly technical, but still intuitive example that shows how subtle this can be. Consider the fine structure constant alpha, which governs how strongly electrons interact with photons. Many spectral lines' energies scale slightly differently with alpha. If alpha were different in the past, lines like the doublet of magnesium and the fine structure splitting in iron would shift relative to one another, not just all together. Astronomers exploit this by using the many multiplet method to compare numerous transitions from different elements, and thereby place tight bounds on alpha's variation. Those bounds are often phrased as delta alpha/alpha, less than a few parts in 10^6 or better over cosmological times. That is an extremely small wiggle room. A shrinking model that relies on changing alpha must live in that narrow corridor or be inconsistent with the data. Another example involves the CMB temperature at high redshift. Suppose you find an absorption system at redshift Z, and you measure excitation states of certain molecules or atoms that are sensitive to the local radiation temperature. In an expanding universe, the CMB temperature at that redshift should be T0, 1 plus Z. Observations of CN absorption in some systems and fine structure excitation of certain species in others have measured the CMB temperature at various redshifts and found it to track that scaling within errors. Any model that claims the observed redshift is due to shrinking rulers must explain why the background radiation scales like 1 plus Z, either by having the metric behave as if it's expanding for radiation, or by invoking an alternate photon production or thermalization mechanism that produces the same scaling. That is again a strong constraint. Now imagine an observer in the far future discovering that all distant galaxies look slightly different compared to local ones. Would that be evidence for shrinking, expanding, or something else? The observer would have to translate those differences into a set of dimensionless, frame-invariant quantities before drawing physical conclusions. That's why cosmologists invest so much effort into precise, redundant measurements. They let us infer frame-invariant conclusions rather than artifacts of a particular coordinate choice. Given how many observational levers exist, what would be the most promising new experiments or observations to decisively test or detect any tiny shrinking-like phenomenon? Here are a few directions that look especially powerful. Continued and improved high-resolution spectroscopy of quasars and distant molecular clouds. Instruments that stabilize calibration at the level of centimeters per second and that control systematics carefully can push constraints on variations in alpha and mu still further. The upcoming generation of extremely large telescopes, ELTS, with laser frequency comb calibration is crucial here. More precise measurements of the CMB spectrum and its temperature at various redshifts. Although COBE established the CMB spectrum to high precision, future missions could detect tiny deviations that would betray energy exchange or non-standard photon processes. Additionally, more measurements of the CMB temperature using independent astrophysical tracers at a range of redshifts strengthen constraints. Better mapping of the baryon acoustic oscillation scale across a broad redshift range. BAO offers a standard ruler anchored in early universe physics, comparing BAO distances to supernova distances, and the CMB provides strong consistency checks. Projects like DAISY and Euclid are already moving us forward here. Gravitational wave observations targeting primordial backgrounds and the redshift evolution of inspirals. Space-based detectors and pulsar timing arrays expand the frequency range and could reveal relics of an early contracting phase or otherwise unusual dynamics. Ultra-precise local tests. Atomic clock networks, torsion balance searches for fifth forces, and lunar laser ranging. These sharpen constraints on any local manifestation of the fields or couplings that a shrinking model might invoke. laboratory experiments that test screening mechanisms and scalar field couplings under varied densities. If a scalar field hides cosmological evolution by being suppressed in dense environments, experiments that vary environmental density could reveal its coupling. These experiments combine terrestrial and astronomical tools. That is the virtue of modern cosmology. The laboratory and the sky complement each other because the same fundamental physics underlies both. There's an intriguing conceptual possibility worth mentioning that sometimes gets lost in observational lists. Shrinkage could be an emergent, effective description of more complex microphysics. Just as temperature is a macroscopic concept that emerges from microscopic motion, cosmological scale behavior could be an emergent phenomenon of some underlying degrees of freedom. In such a scenario, shrinking might describe an effective rescaling of emergent rods that occurs when those underlying degrees of freedom evolve. That makes the idea harder to test directly because you must identify the microphysical basis and how it couples to ordinary matter. Yet the effective viewpoint also makes a testable prediction. The emergent description will break at some scale or in some regime, producing anomalies. Finding such anomalies could hint at deeper layers of physics, whether those layers are quantum gravity effects, extra dimensions, or novel condensates. Finally, the very process of scrutinizing shrinking models highlights a virtue of scientific thinking, being forced to specify how a claim connects to empirical data. The universe is shrinking is a simple sentence, but physics is not done in slogans. It is done in models with equations and measurable predictions. When you try to convert an evocative phrase into a model, you are pushed to identify the independent things you can measure, the invariance of the theory, and the specific mechanisms that would cause observables to change. That process is valuable whether the model survives or not. It clarifies which experiments are decisive, it suggests new measurements, and it deepens our understanding of existing observations. So, what remains to be explored? On the theoretical side, tighter formulations of scalar field and modified gravity models that produce shrinkage-like phenomenology while being naturally screened locally are an open area. On the observational side, the continuing improvements in precision, both in the lab and in the sky, will either shrink the window for such models still further or, potentially, reveal tiny anomalies that demand new physics. In either case, wrestling with the question of shrinkage sharpens our tools and our questions about the universe. Let me leave you with a hands-on way to think about the stakes. Picture three independent sets of rulers: atomic spectra, supernova time-dilated light curves, and the Bow scale. In the standard expanding model, all three change with redshift in ways that are calculable from the expansion history and agree across the board. In a shrinking model, you must change either the rulers themselves, the physics that sets spectral lines or supernova timing, or the way photons and gravitational waves propagate, so that their travel encodes the different histories. And you must do it so that the three different measures continue to agree. That agreement is hard to maintain by accident. So the shrinking hypothesis is an invitation to construct a detailed mechanism connecting microphysics, astrophysics, and geometry. An invitation that, if accepted, either yields a new, testable theory or helps confirm why the expanding picture is so robust. We're not done exploring these ideas. New instruments, new data, and new theoretical tools continue to refine the picture. But the interplay of independent probes, laboratory experiments, and theoretical consistency is what ultimately converts colorful speculation into reliable knowledge. If a shrinking universe is hiding in the data somewhere, the net of independent tests will, over time, make that hiding place smaller and more exposed. If it's not hiding, the exercise of looking, of designing experiments and thinking through consequences only makes the foundations of cosmology firmer and the questions more interesting. One of the most useful ways to move forward with this question is to ask, what would we actually see if a non-standard, shrinking mechanism were at work? That forces us to imagine specific experimental signatures and then check whether we already see them or not. We've already gone through the big-ticket constraints: supernova time dilation, the CMB blackbody spectrum and acoustic peaks, baryon acoustic oscillations, Big Bang nucleosynthesis, and spectral checks on atomic constants. Now let's drill down into how new measurements and better instruments sharpen those tests, what kinds of subtle fingerprints a shrinking-like model might leave, and where current anomalies in cosmology could, at least in principle, hint at something unexpected. Start with the fundamental laboratory toolkit, because cosmology doesn't float above the lab, it rests on it. Atomic clocks, frequency combs, ultra-stable lasers, and clever spectroscopy are the kind of precision tools that can detect tiny drifts in the relationships between physical quantities. Imagine a scalar field that slowly changes the electron mass or the strength of electromagnetism. That would shift atomic transition frequencies by different amounts depending on the quantum numbers of the states involved. Modern optical clocks based on different transitions, for example, one clock using an aluminum-ion transition and another using a terbium, can be compared continually. If they drift relative to one another, that's a red flag that some underlying constant is changing. In practice, comparisons have become so sensitive that many proposed shrinking mechanisms are already squeezed by these data, unless they come with a built-in way to hide local effects. That hiding mechanism, often called screening in the theoretical literature, is itself a testable concept. The basic idea is that a field could have different effects depending on the local environment. In the high-density environment of a laboratory, the field's influence would be suppressed, while on cosmic scales the field's slow evolution would be active. This is a neat theoretical trick, but it's not magical. Screening mechanisms generally produce their own measurable consequences. For example, they may predict slight violations of the inverse square law of gravity at certain distance scales, or they may cause subtle differences in how stars of a given mass burn their fuel. So we can hunt for signs of screening in precision force experiments, in stellar evolution data, and through careful checks in the solar system. If we find no sign of the screening's fingerprints where they should be visible, that reduces the plausibility of the whole scheme. Switch from the lab to the sky, and the next natural place to look is the detailed structure of spectral lines from distant gas clouds. When astronomers measure redshift, they don't just read one line. They measure many lines from different atoms and molecules. Each transition has a different dependence on the fine structure constant and on the proton-to-electron mass ratio. If only the metric of spacetime were stretching, all lines from the same cloud should shift together. If the underlying constants were changing, different lines would shift by different relative amounts. That's why the many-multiplet method, using many transitions at once, is so valuable. It disentangles pure kinematic redshift from physical changes in atomic physics. It's also why the controversy over early claims of a varying fine structure constant largely came down to careful instrument calibration and systematics. Spectrographs must be calibrated to extreme precision. A tiny wavelength drift in the instrument can masquerade as a change in alpha. Improving calibration, using laser frequency combs for example, is reducing this experimental uncertainty, and these improvements directly close loopholes for shrinking-like models. Let's look next at cosmological standard rulers and standard candles. Supernovae of type Ia behave like standardizable candles. Their peak brightness can be calibrated so they serve as distance indicators. Their light curves get stretched by time dilation in an expanding universe, and the observed stretching matches the expected, 1 plus z, scaling beautifully. If the apparent redshift instead came from, say, atoms being different in the past but the geometry itself not expanding, you would still need to explain why the supernova time sequences stretch exactly like their spectral redshifts. That's a more subtle requirement than simply shifting wavelengths. It couples the microphysics of the emitter to the timing of large-scale astrophysical processes. Similarly, the baryon acoustic oscillation scale, the imprint of primordial sound waves, provides a ruler anchored in early universe physics. The Bow scale, as measured in the clustering of galaxies at different redshifts, matches the same scale inferred from the CMB, within error bars. Maintaining that agreement is challenging for a model that alters particle masses or couplings in an ad hoc way. Another observational arena where a shrinking hypothesis could leave a trace is the pattern of small deviations in the CMB, the precise arrangement and relative heights of the acoustic peaks. Those peaks are sensitive to the ratio of baryons to photons, to the total matter density, and to the precise expansion history near recombination. If some exotic process altered how photons lose or gain energy over cosmic time, you would likely see distortions in the peak structure or in the damping tail at small angular scales. So far, the Planck satellite and other CMB experiments have not found such distortions beyond very tight limits. That rules out a range of models that would change photon energies or numbers during the period from recombination to today. Gravitational waves are a new and promising window on this discussion. They carry information about cosmic history that's complementary to photons. If there were a contracting phase before our expansion, a bona fide shrinking epoch followed by a bounce, the spectrum of primordial gravitational waves would be different from the spectrum predicted by simple inflation. Some bounce models predict suppressed gravitational wave amplitudes at certain frequencies or oscillatory signatures in the spectrum. Future space-based detectors like LISA and advances in pulsar timing arrays could in principle detect those imprints. If we saw a gravitational wave background consistent with a non-inflationary contraction and bounce scenario, that would be a dramatic clue. Conversely, if the gravitational wave background matches inflationary expectations tightly, that squeezes bounce models into narrower corners. It's worth examining a concrete hypothetical signature that a contracting then bouncing universe might leave: an oscillatory modulation of the primordial density power spectrum. If the universe contracted and then rebounded, some residual phase information could survive, producing small ripples in the distribution of primordial fluctuations. Those ripples could manifest as mild oscillations in the matter power spectrum measured by galaxy surveys, or as particular non-Gaussian patterns in the CMB. Large galaxy surveys like Daisy and Euclid, when combined with CMB data, are getting precise enough to see or rule out mild oscillatory features. So the hunt isn't just for gross differences, it's for subtle telltale shapes in correlation functions and power spectra. We should also talk about the kinds of astrophysical mimicry that can fool us if we're not careful. Nature throws up phenomena that can look like new physics unless we model them properly. For instance, dust extinction, galaxy evolution, and selection effects in surveys can all systematically bias distance estimates and spectral measurements. Early claims of strange anomalies often evaporate when astronomers discover a previously neglected systematic effect. That's why cosmology increasingly emphasizes blind analyses, cross-checks with different instruments, and multiple independent probes. If a suspicious signal shows up in one instrument or method, seeing whether it appears in other, independent data sets is crucial. A true physical effect that ties into the core of cosmology should appear consistently across different kinds of measurements. An instrumental artifact typically will not. This is also the reason the Hubble tension, the mismatch between the local direct measurement of the Hubble constant and the value inferred from the CMB assuming the standard cosmological model, has generated so much attention. It's an anomaly that has withstood increased scrutiny of systematics on both sides, and so people are legitimately exploring whether it points to new physics. Could a shrinking-like mechanism explain the Hubble tension? It's extremely difficult. Simply reinterpreting distances through changing units tends to produce inconsistencies with other independent measures. What many researchers do instead is look for new early universe physics that changes the sound horizon at recombination, thereby altering the CMB-inferred H0 without wrecking other physics. That's an example of how the scientific community frames anomalies. Start from the measurements, ask what minimal change to the model could reconcile them, and then test whether that change disrupts other successful predictions. If you tried to use a full-blown shrinking scenario to patch the Hubble tension, you'd find it easy to create one agreement and hard to preserve dozens of others. That doesn't mean we shouldn't look. The tension could be a harbinger of real new physics, but it does show the bar for a radical reinterpretation is high. Another aspect to consider is the role of black holes and their thermodynamics. Black holes are laboratories for extreme gravity, and their evolution has implications for cosmic entropy and the arrow of time, two themes that come up loudly when considering contraction and cycles. If the universe were to shrink toward a high-density state, black holes would play a central role in the entropy bookkeeping. Do they survive a bounce? Do they evaporate and lose their information? Penrose's conformal cyclic cosmology criticizes the standard inflationary picture by focusing on the fate of black holes in the far future, and on how massless radiation might be the bridge to a new eon. These are speculative, deep questions that touch on quantum gravity and information theory. They're not easy to test, but they illustrate that any serious cosmological model, shrinking or not, has to grapple with how entropy evolves through extreme epochs. This isn't an optional philosophical add-on. It constrains the consistency of the whole model. Turning to the practicalities of experiments and surveys, the way we design observations today already anticipates many of the potential pitfalls a shrinking hypothesis could exploit. Survey strategies increasingly build in redundancy. Multiple spectral lines, multiple photometric bands, overlapping instruments with different systematics, and cross-correlation analyses between data sets. That redundancy is intentional because discerning tiny discrepancies, whether they come from subtle changes in constants, from hyperaccurate distance measures, or from early universe imprints, requires multiple independent confirmations. For instance, future ELT-class telescopes will pair high-resolution spectroscopy of quasars with tight calibration via frequency combs. That combination directly addresses earlier systematic problems that led to tentative claims of changing constants. Simultaneously, new CMB polarization experiments will push sensitivity to primordial gravitational waves and B-mode signals that could distinguish between inflation and many bounce scenarios. There's also a data analysis lesson that's worth repeating explicitly: the importance of model-independent checks. Many cosmological conclusions depend on taking a theoretical model and fitting it to data. But it's possible for different underlying realities to produce similar signatures within model space. To be robust, scientists therefore use model-independent or minimally model-dependent observables wherever possible. Examples include measuring the CMB temperature at different redshifts using atomic excitation in intervening clouds, which directly tests the 1 plus z scaling of temperature, or comparing the Bow scale inferred directly from galaxy clustering without assuming a particular late-time expansion history. Model-independent approaches let you ask whether data contain contradictions that no single smooth extension of the standard model can cover, which is precisely the sort of stress test that would reveal a genuine shrinking-like effect. Let's also be clear about the timescales and amplitudes involved. Many exotic scenarios suggest drifts or changes that are slow, parts per million per billion years, say. Detecting those is technically challenging, but not impossible. It's why atomic clock networks and long baseline astronomical time series are vital. Conversely, a dramatic shrinking on short timescales would have catastrophic, unmistakable consequences. Orbits would change, pulsars' timing stability would fail, and radio astronomy pulsar arrays would notice. The lack of any such dramatic signature tells us that if anything is changing, it's doing so very slowly and subtly. That narrows the field of plausible mechanisms to ones that predict tiny drifts, precisely the regime where high-precision instruments are designed to operate. One more point that bears emphasis. When theorists build models where particle masses or couplings evolve, they rarely do so in isolation. Changing one constant often induces secondary effects. For example, altering the electron mass affects atomic sizes, which changes chemical reaction rates, which can change stellar opacities and therefore the light emitted by stars. Those consequences propagate into astrophysical observables, stellar spectra, lifetimes, and population ratios that astronomers can measure. That interconnectivity of physics is both a constraint and an opportunity. It's a constraint because it closes many possible loopholes for models that try to hide in one type of observation while changing others. It's an opportunity because it gives us many different detectors for the same underlying phenomenon. A change that might be barely detectable in a laboratory clock could be more visible in stellar evolution or in spectral patterns across many stars. On the theoretical side, one of the cleanest conceptual frameworks for thinking about alternative scaling behaviors is to use conformal transformations, or to consider different frames, for describing gravity coupled to scalar fields. In one frame, the metric may evolve in a way we interpret as expansion. In another frame, particle masses vary and the metric looks different. These are more than mathematical hair-splitting. They illustrate how different physical interpretations arise from the same equations, depending on what you treat as the fixed yardstick. But frame equivalence only goes so far. Observable predictions that are frame-invariant, dimensionless ratios, spectral shapes, or timing relations ultimately decide which pictures are physically equivalent and which are not. That's why experiments that probe dimensionless quantities, like alpha or mu, are so decisive. We should also reflect on the interplay between cosmology and particle physics. Many of the fields that cosmologists invoke to explain cosmic acceleration, varying constants, or cycles are scalar fields. Those fields might arise naturally in extensions of the standard model, in string theory constructions, for example, or they might be purely phenomenological. If a cosmologist proposes a field that gradually changes the electron mass, particle physicists will immediately ask whether that field couples to known particles in a way that violates laboratory constraints, or whether it could mediate detectable fifth forces. Bringing together particle physics experiments, precision atomic measurements, and cosmological data gives a much richer constraint network than any one domain alone. That's one of the strengths that has emerged in modern physics. The cross-pollination of seemingly distant fields yields far stronger tests than any could provide individually. Another fertile area of research is the search for small-scale anomalies that could indicate unusual early universe physics. For instance, certain bounce scenarios predict enhanced formation of small primordial black holes in restricted mass ranges. Those black holes could produce a stochastic gravitational wave background, microlensing signatures, or specific cosmic ray signatures if they evaporate. So the hunt for primordial black holes, via lensing surveys, gravitational wave searches, and high-energy astrophysical observations, doubles as an indirect search for exotic early universe histories that may include contracting epochs. If we zoom out a little and ask what kinds of philosophical lessons this whole exercise teaches, the relational nature of measurement stands out. Saying the universe is shrinking is not a single, unambiguous statement. It depends on what you choose to hold fixed, your rulers, your clocks, or the dynamics of certain fields. Science advances by turning such statements into precise, testable hypotheses about relationships between measurable quantities. We can't measure an absolute scale, we measure ratios and correlations. That operational viewpoint guards us against getting seduced by elegant words and instead focuses attention on measurable consequences. A credible shrinking model must therefore translate its poetic claim into a set of predicted relations. Say, how the fine structure constant changes as a function of redshift, and how that would affect a specific list of observables. Only then can we test, refine, or falsify the idea. Before moving on to specific observational campaigns that are likely to be decisive in the near future, it's useful to give an example that ties together several threads. Suppose a theorist proposes a scalar field that couples preferentially to electrons and tunes the coupling so that the electron mass decreases by 1 part in a million over 10 billion years. What would we expect to see? High-resolution quasar spectra would show slight relative shifts between molecular lines that depend strongly on the electron mass, and other lines that depend mostly on nuclear masses. Atomic clocks on Earth using different atomic species might show tiny drifts in comparison over a decade if the coupling isn't fully screened locally. Stellar spectra could show minuscule deviations from predicted line ratios. CMB physics might be largely unaffected if the field's influence is small at recombination, but Big Bang nucleosynthesis constraints could bite depending on the field's behavior at those early times. Lensing and bow measurements would probably remain consistent with standard distances unless the field also couples to gravity. So a combination of astrophysical spectroscopy, laboratory clock monitoring, and careful early universe constraints would jointly test the hypothesis. That example illustrates how a single modest proposal quickly fans out into a web of experiments and observations, and why the web is so constraining. Looking ahead, which observational campaigns are likely to tighten the net or reveal new cracks? A few stand out. High-resolution, ultra-stable spectrographs on giant telescopes. These will push sensitivity to variations in constants to new levels by observing many quasar absorption systems and molecular clouds across a wide range of redshifts with exquisite calibration. Next-generation CMB experiments. CMBS-4 and other projects will sharpen measurements of primordial fluctuations, improving constraints on primordial gravitational waves and on subtle spectral distortions. Large-scale structure surveys, DAISY, Euclid, Rubin Observatory, and future galaxy surveys will measure the bow scale and growth of structure across cosmic time, providing an increasingly precise geometric and dynamical map of the universe. Gravitational wave observatories across frequency bands. LISA, future ground-based detectors, and pulsar timing arrays will probe primordial backgrounds and astrophysical populations that could betray unusual early universe behavior. A global network of atomic clocks and precision laboratory searches for fifth forces, extending the time baseline and environmental variation in experiments tightens bounds on any cosmological field that might try to hide locally. Each of these efforts attacks the problem from a different angle. That multiplicity is essential. A model that manages to slip past one kind of test will likely be caught by another. That's both a pragmatic and a philosophical point. The interconnectedness of physical phenomena is what makes cosmology such a powerful science. At the same time, scientists must remain open to surprises. Precision measurements often reveal unexpected small discrepancies. Sometimes they point to previously unknown systematics that get ironed out, and sometimes they reveal genuine new physics. The history of cosmology is full of both kinds of outcomes. The microwave background itself was an unexpected discovery that reshaped the field, and more recently, the Hubble tension has provoked serious, creative work. If a shrinking-like signal hid anywhere, the route to discovering it will be through careful accumulation of consistent, cross-checked anomalies that survive attempts to explain them away with mundane causes. Finally, there is an aesthetic dimension that matters in practice, even if it's not decisive on its own. Physicists prefer explanations that are not wildly contrived, that fit into broader theoretical frameworks, and that don't require fine-tuning unless forced by data. The standard cosmological model, with expansion from a hot, dense early phase, inflationary ideas for the initial conditions, cold, dark matter to explain structure, and dark energy to account for late-time acceleration, is economical in that it uses a handful of parameters to explain a great many observations. Alternatives need not be ruled out simply because they are complicated, but they do need to earn their keep by solving problems the standard model cannot, or by making new, testable predictions that are confirmed. That pragmatic attitude drives the focus toward experiments that discriminate between plausible alternatives, rather than indulgent, unfalsifiable speculations. So when you return to the question, could the universe actually be shrinking? You can do so armed with practical tools for thinking. You can ask whether the claim is a relabeling of units or a physical assertion about dimensionless quantities. You can map out the set of independent observational probes that would be sensitive to the claim, and you can follow through on the connections between laboratory physics, astrophysics, and cosmology to see whether the claim survives. That way of working, precise, empirical, and relational, is what turns evocative ideas into scientific knowledge. The rest is hard, patient work, building instruments, collecting data, analyzing it carefully, and letting the universe tell us what it's doing. That hard, patient work, building better instruments, designing more clever tests, and comparing independent measurements, is exactly the path that would reveal whether any tiny, strange effect is hiding in the data. So let's talk about what that investigative program looks like in practice. What kinds of small anomalies might genuinely be interesting, and what it would mean for our picture of reality if evidence for a shrinking effect ever accumulated to the point that it could not be explained away. First, think about how scientists behave when an odd measurement shows up. You don't instantly rewrite textbooks. You do the opposite. You assume for a long time that the anomaly is a glitch, and you try hard to find mundane explanations. That cautious approach is a feature. Instruments have quirks, software can introduce subtle biases, and the universe throws up complicated astrophysical foregrounds. So the typical life cycle of an anomaly is detection, cross-checks with independent instruments and methods, hunts for systematics, refinement of the analysis, and only then, if the signal persists through multiple independent lines of inquiry, does the community start to consider new physics seriously. That process is why a single unusual measurement, say, a tiny drift in an atomic clock comparison or an odd line shift in one quasar spectrum, doesn't suddenly imply the universe is shrinking. What matters is when many independent measurements, made in different ways and at different times, point at the same odd behavior that cannot be connected to instrument or astrophysical effects. Now suppose such a coherent pattern did emerge. What would be the first steps? Researchers would begin by asking whether the effect is dimensionful or dimensionless, in plain language, whether it depends on the units we use or whether it shows up in pure ratios. A true physical discovery needs to show up in dimensionless ratios, because changing units alone cannot create physical consequences. For example, if a molecular transition frequency divided by another frequency changed over cosmic time, that would be physical. If instead everything measured in meters and seconds changed in concert, that might simply be a unit redefinition and would not fundamentally alter physics. So tests that compare different kinds of clocks, different spectral lines, and different astrophysical clocks, like pulsars or the cadence of certain types of variable stars, are especially powerful. They give you a web of ratios that can't all be faked by a trivial relabeling. Which particular instruments and observations would be decisive? The short answer is the ones we're already building and the ones people are planning. Ultra-stable spectrographs on the next generation of giant telescopes will measure quasar absorption lines with unprecedented precision, making it possible to detect or constrain minute drifts in atomic parameters over billions of years. Networks of optical atomic clocks are already sensitive enough to detect tiny temporal drifts in fundamental constants over years. Extending those networks and improving stability increases sensitivity to slow cosmological trends. Pulsar timing arrays, networks monitoring millisecond pulsars across the sky, serve as cosmic clocks over years and decades, and can reveal subtle changes in the propagation of signals across the galaxy. On the cosmological side, experiments that map the cosmic microwave background more precisely or reach different angular scales will continue to be telling. The CMB spectrum is a pristine thermal fingerprint. Even small energy exchanges with matter or fields after recombination would leave distortions. Future CMB missions aimed at measuring spectral distortions at levels far below current limits would either narrow the room for tired light type processes or reveal hints of exotic physics. Baryon acoustic oscillation surveys and wide-field galaxy maps like those planned for the Rubin Observatory, Euclid, and Daisy give robust geometric measures that can be compared with supernova distances. Gravitational wave observatories, both ground-based and space-based, open a qualitatively new channel. They let us probe how the universe affects ripples in space-time, not just photons. Since gravitational waves interact differently with fields and matter than photons do, a discrepancy between what gravitational waves and light tell us about distances or the expansion history would be a smoking gun for new physics. So the experimental program is broad and complementary. That breadth is exactly what makes a real shrinking-like effect hard to hide. You need a coordinated explanation that simultaneously satisfies laboratory tests, local gravitational tests, stellar and nuclear physics, cosmological temperature and spectrum measurements, and large-scale structure. That web of constraints is why most of the clever early alternatives to expansion were eventually ruled out. But let's be fair. Some ideas survive in refined forms that respect current limits while still offering non-trivial predictions. Those are the models that merit attention because they're disciplined. They make specific, testable predictions and they leave room for discovery. What would such a discovery mean for physics? That depends on the nature of the effect. If we found that a dimensionless constant, say the fine structure constant that controls how strongly electrons interact with light, was changing slowly over cosmological time in a way that could not be explained by measurement error, that would be huge. It would tell us that what we thought were fixed inputs to chemistry and atomic structure are actually evolving, which would have consequences across physics and chemistry. Laboratory chemistry would hardly change tomorrow. Any effect would be tiny on human timescales, but our understanding of the fundamental laws would shift. Particle physicists would scramble to embed a time-evolving coupling into a deeper theory, perhaps by invoking a new field that couples to known particles. Cosmologists would study how that field affects structure formation, the CMB, and nucleosynthesis. Theorists would have to ensure that the field doesn't mediate a detectable fifth force or spoil successful predictions of stellar behavior. In short, it would rewrite the interface between particle physics, astrophysics, and cosmology. If the discovered behavior were instead something that specifically mimicked expansion, for example, if atomic sizes changed in a way that made distant light appear redshifted, we'd face an urgent conceptual cleanup. The first job would be to show that this effect cannot be reinterpreted as the usual metric expansion in a different mathematical frame. In practice, this would likely mean developing a model where particle masses or couplings evolve, and then showing that this model produces observational signatures that are not reproduced by the standard expanding model. Only then could we say we had evidence for a physically different scenario. That's why the community would demand multiple independent confirmations. Matching a redshift distance relation is necessary but not sufficient. Matching the CMB, supernova time dilation, BAO, nucleosynthesis, and local laboratory constraints all together is the real test. A discovery like this would also invigorate searches for new fundamental fields. The simplest way to get slowly changing constants in field theories is to introduce scalar fields that vary with time. Those are common in theoretical extensions of the standard model, in particle physics, and in models of dark energy. If a scalar were found to cause a tiny change in electron mass, for example, people would ask whether the same field could be tied to dark energy, or to dark matter, or to supersymmetry breaking. The connection could be accidental, but it might point to a deeper unity. That kind of cross-fertilization is how progress often happens. A surprising measurement in one domain ripples into many areas of theory and experiment. Now let's imagine another, more dramatic scenario. Suppose we detected a clear signature that a contracting phase preceded the hot Big Bang, a real shrinking phase in cosmic history that ended in a bounce and left a detectable imprint. What would that look like? The clearest possible clue would probably be a gravitational wave signature inconsistent with simple inflationary predictions, yet consistent with a bounce. Bounce models can produce distinctive patterns in the spectrum of primordial gravitational waves and in the statistics of primordial density fluctuations. For instance, some bouncing scenarios predict specific oscillatory features, small wiggles, in the power spectrum of initial fluctuations or particular forms of non-Gaussianity, deviations from the simple random Gaussian fluctuations predicted by many inflation models. If next-generation CMB polarization experiments and gravitational wave detectors together found such a pattern, it would provide strong evidence for non-inflationary early universe dynamics. Detecting such relics is extremely challenging, but feasible in principle. The reason it's plausible is that gravitational waves interact very weakly with the rest of matter and radiation. Once produced in the early universe, they propagate largely unscathed, carrying information about their source. That makes gravitational waves a particularly clean probe of very early cosmic epochs, including any contracting phase. So, one concrete frontier in testing contraction plus bounce ideas is the continuing improvement in gravitational wave sensitivity across different frequency bands, from the nanohertz band probed by pulsar timing, arrays to the millihertz band targeted by space-based detectors. There's another kind of signature that a non-standard early history might leave: a mismatch in the baryon acoustic oscillation scale as inferred at different redshifts or using different methods. Because the bow scale is a physical length set at recombination, any change in the early universe dynamics that affected the sound horizon would shift how this ruler maps into observables. That's one reason the Hubble tension debate has driven so much work. If some early universe physics changed the sound horizon slightly, it could reconcile local measurements of the Hubble constant with CMB inferred values. That same lever, changing the sound horizon by altering early time physics, is how some people try to accommodate a variety of cosmological anomalies without giving up the successful late-time expansion picture. So bow data, particularly at a range of redshifts, remain a crucial cross-check. One more empirical point before we move back to big-picture thinking: it's not enough to find a single anomalous quantity. The real power of cosmology comes from redundancies, from the fact that the same physical constants and the same early universe events affect many different observables. That redundancy produces cross-checks. For instance, if some new physics alters the proton-to-electron mass ratio and thereby affects molecular spectra, it will also influence molecular cooling in the early phases of star formation, which might change the properties of the first stars, which in turn can be constrained by observations of very old stars and by chemical abundances in old stellar populations. That chain of consequences is why a genuine departure from the standard model tends to leave fingerprints in many arenas. Now, beyond immediate observational and theoretical implications, let's consider some conceptual and philosophical consequences. One of the recurring lessons of physics is that what looks like a radical reinterpretation often becomes uninteresting once you realize it's a matter of description. If the shrinking universe can be re-expressed as a simple change of units or as a mathematically equivalent relabeling in a different coordinate system, it's not a new physical discovery so much as a semantic shift. The deeper, more interesting possibilities are the ones that change dimensionless ratios. Those are genuine physics statements. Recognizing that distinction is crucial because it helps separate declarations that demand new physics from ones that are merely different bookkeeping. Another deep question relates to ontology. Do space and time exist independently of matter, or are they relational constructs that only have meaning in the presence of material content? Historically, philosophers like Leibniz argued for a relational view, that spatial relations are about distances between things, not about a background stage, and Newton's absolute space was a competing idea. In modern physics, general relativity fuses matter and geometry in an intimate way. The distribution of matter and energy tells spacetime how to curve, and that curvature tells matter how to move. Debates about whether the universe is really expanding or whether rulers are shrinking are, in a sense, modern incarnations of this philosophical dispute. The practical answer scientists use is operational. Focus on observables and frame invariant quantities. But the philosophical undercurrent remains fascinating because it guides how we interpret cosmological models and which mathematical transformations we consider physically significant rather than mere relabelings. If the scientific community did eventually accept a model in which some quantities vary, in which, for example, particle masses evolve over cosmological time, we'd also need to update how we teach physics. Textbooks would add discussions about coupling to scalar fields and about how standard textbook constants can emerge from deeper dynamics. But the day-to-day chemistry in the lab and the mechanics of a swinging pendulum would remain unchanged for practical purposes. Any cosmological drift would be tiny on human timescales. So, a discovery of evolving constants would be monumental for our understanding of the universe, but modest in its practical implications for ordinary life. There's a broader methodological point here that's worth underscoring. Asking, could the universe be shrinking, is the kind of question that forces scientists to sharpen their definitions and their tests. Whether the answer is no or yes, but only in a particular frame or yes, and here's what that would imply. The act of constructing rigorous alternatives strengthens the field. It pushes instrument builders to reduce systematics. It forces theorists to write down models with clear predictions, and it trains researchers to think about which quantities are truly measurable. That intellectual discipline is valuable in its own right because it improves the quality of all science, not just cosmology. Let's take a moment to consider the kinds of anomalies that could plausibly arise and how one would adjudicate among explanations. An anomaly might first appear as a slight discrepancy between different measures of distance. One group might measure H0 locally using Cepheids and supernovae, and find a higher value than another group infers from the CMB and a standard cosmological model. That's what's happened in the Hubble tension. Several threads of explanation are possible: unrecognized calibration errors in local distance ladders, subtle biases in how supernova samples are selected, or new early universe physics that changes the sound horizon. Similarly, a tiny discrepancy in spectral lines could be a calibration artifact, unmodeled gas motions in the absorber, or a real change in atomic parameters. The way to disentangle these is to ask for independent, differently designed measurements. If the anomaly is reduced or disappears with improved instrumentation or a different analysis method, it was probably systematic. If it persists and shows up across different instruments and methods, then it starts to look like new physics. How would scientists communicate such a discovery to the public? Carefully and with context. Responsible scientists avoid dramatic headlines until multiple independent confirmations exist. They'd explain what was measured, how the measurement compares to previous work, what systematics were considered and ruled out, and what plausible theoretical frameworks could explain it. They'd also explain what the practical implications are, usually none for everyday life, and what the next steps are. That balanced process, cautious public communication coupled with rigorous cross-checking in the scientific community, has been the pattern for major discoveries from the detection of the cosmic microwave background to the discovery of gravitational waves. To close the loop and bring this back to everyday intuition, let's revisit a simple image. Suppose every object in your house shrank by 1 part in a million each year. You wouldn't notice on a day-to-day basis. Key fits would remain the same. Your clock would still tick the same number of ticks per second by your own standard, and a ball would still fall the same way on your house's floor. But if you compared your local meter stick to a meter stick made and left by your great-grandparents 100 million years ago, a fanciful situation, but conceptually useful, you might discover that their meter aligns differently with some absolute standard. In cosmology, we have an analogous network of great-grandparent standards. The CMB, primordial nucleosynthesis, the Bow scale, and the ancient light from quasars act as benchmarks that let us probe whether subtle changes accumulate over cosmic time. Those benchmarks are what make the universe an empirical laboratory for testing whether anything substantial is shifting. Finally, imagine that future telescopes and detectors do find small deviations in multiple independent channels that consistently point toward some kind of slow, cosmological scale change in particle properties or spacetime behavior. The resulting theoretical developments would likely be as transformative as the acceptance of quantum mechanics or relativity. They would force us to rethink deep assumptions and likely lead to new physics that connects cosmology with particle physics, and perhaps even with quantum gravity. The practical roadmap to that possibility is clear. Improve instrumentation, build redundancy into observations, refine theoretical models to make crisp predictions, and remain disciplined about distinguishing real effects from instrument or astrophysical systematics. All of this is to say that the question, could the universe be shrinking, is less about sensational alternative narratives and more about the scientific method at work. Pose a bold idea, derive specific, falsifiable consequences, and then test those predictions with the most precise tools we can build. Whether the answer ultimately endorses expansion, reveals a new subtle evolution of constants, or uncovers an unexpected bounce in the deep past, the process of asking and testing is how our picture of the cosmos gets sharper. Keep an eye on precision spectroscopy, pulsar timing, gravitational waves, and improved CMB and large-scale structure surveys. The next decade of data will keep tightening the net, and if anything truly novel is hidden, that's where it will be found.